Hello everyone, my name is Manjani and today I'm going to talk about my final project that I've done for this subject, malicious AI and dark side security. My topic is a hybrid classical quantum neural network with adversarial testing and stress. Right. So first, let me present the results. Right. So my team has not really achieved a good result for my given project here. As you can see with the clean data set without any quantum like noise, it's like accuracy of 95. When there's no defense and adversarial attack starts, it's at 2% accuracy with 6.87 loss. And with adversarial defense training together with data set, we only got a measly 43% of accuracy compared to the original collab that we have. We have a clean of 95% accuracy, no defense attack of 2% accuracy, and with the adversarial training, we get 97% of accuracy. So I'll walk you through what I went through, and I'll document my whole process with this. So first, over here, we have to choose like the type of attack that we want to do for our given dataset. And the dataset I've chosen here is the MNIST dataset. And the attack that I've chosen is also the FGSM CW attack here with 10 epochs. And so what I've done for this project is that instead of using the hybrid neural network that's provided here, where they only use the fixed number of quantum circuits, where it's not really trainable per se, I wanted to make it dynamic and adapt to the given input however it wants. And I built a penny lane based quantum module over here. Then it learns from the data itself and how it can actually work together with the CNN to build trainable weights. So then I also evaluate the system together with consistent compound attack, which is the FGSM with CW attack over here across all phases with the clean phase, no defense phase, and also post-defense phase, which is after it's done adversarial training to keep comparisons fair between my data in my project and the original Google Colab here. And for the original Google Colab, you're initially trained on the full MNIST dataset, but because of some limitations that I'll get into later, I've tricked it to only take 5,000 test inputs with 2,000 adversarial training data over there. Okay, so most students in this subject decide to go with deepfakes because it's quite popular now, right? And for me personally, I wanted to try and do something different, so I gravitated towards trying out adversarial attacks and just seeing how I can further advance that field. And I found this collab, which is under Eric York. This one over here. And this one is quite interesting, right? Because it combines like the quantum layer together with the classical neural network together to build a hybrid neural network over here. But because they used a fixed amount of quantum layers that they didn't change at all, like it's fixed over here. Like the circuit is like fixed rotations, theta and phi. I want to make that learnable, right? And this made it really difficult because of the resources that I needed to train from each individual input itself. So here you can see that's the quantum layer that I've further modified. So a circuit, it kind of takes the input from the number of qubits that we want. And I also integrated some noise. I injected noise to it so that it can further do more adversarial training at the start together to make it more robust and better for training. And then we also have the CNN over here, the classic CNN, which I didn't touch as much, didn't modify it here. And then we have the HMN over here, hybrid neural network. So this one, it takes the quantum layer together. As you can see, that quantum layer function is called, and it trains it together with the alpha and beta. So they're both like how much emphasis to give on the quantum part and how much emphasis to give on the CNN. So all of them are like more dynamic now, and it's supposed to actually make the model more difficult to be attacked by adversarial data sets, right? Because it's harder for us to actually predict and know what kind of inputs we want to give the model itself. But if it's like the original one, that one they use the fixed quantum circuit, and once you figure that out, you can actually just like exploit the system. So here we have the hybrid model, and this one I used it to debug, so we can see like the parameters here and the size, and I also can see like the gradient, whether how much emphasis is being placed on the quantum circuit, like the quantum layer for mine, and how much emphasis is being placed on the CNN itself. And here we also have the MNIST dataset, and I fixed it to only MNIST dataset compared to the like multiple dataset options available because I want to keep things simple for my case. And I actually wanted to do the full dataset, but I realized halfway through that actually doing unique quantum layers for each input itself is very resource intensive. So even with 5,000 training size, when I want to do it for adversarial training, it took me like almost 4 hours to even run to train the model itself. So it's very time consuming, and I did not expect it from the original quantum hybrid CNN from the author, because that ran in like less than 1 second. Then as we go through here, we print the images. You can see once we train the model over here, and we trained it, you can see in the epochs 1 what the model actually predicted at first. So it started from 0.36, then jumped to 0.8, so on and so forth. As you can see, by the end we have 0.95 training accuracy and 0.135 training loss. So that's actually pretty good for a clean model, right? Then we want to try to attack it, right? So we have the fresh model over here, and then we can see that out of 2,000 test images that we've given, misclassified only 105 images. So that's about 94.75 accuracy. And then here, we're going to analyze for misclassifications. So you can just see the misclassified data. So this one is, let's say, is 8, but in the raw data 7, which does look quite similar. And then we're going to tackle it with the FGSM full grade assign method, right? So build it and attack it with a clean model, and we perform the attack, and then it took 8 minutes to run, and we got the accuracy of 1.7. So 1,966 data is misclassified out of 2,000 over here. So it's quite bad, right? And we needed to further improve on it. And so we generate the adversarial data sets from here, and then we generate it. So you can see the adversarial images has more noise now. And then we retrain the model over here. So we retrained it, and then we got to train the model. It took us like 4 hours to actually train the model out of like 5,000 data sets. Yeah. After we train the model, we combine the adversarial images that we've generated with the clean images that we have. And then from there, we load the retrained model and we actually attack it again, right? So from here we can see that we got 95% accuracy, which is quite good because you only misclassified like 91 images out of 2000, right? Yeah. And then we evaluate the model, and sorry, yeah, and we notice that the model itself has like, sorry, we notice that the model itself only has like 42.65% accuracy over here, and it's not very good because they've misclassified 1,147 pictures, so that's like half of them, and there are a few reasons for that, right? So the results that I've gotten, and after some analysis that I've done over here, it's most likely that the batches are done because I did like 2 qubits over here, which makes it really difficult to like train because it's such a small qubit number, right? And for a model, you usually want it to be a lot bigger. And due to time constraints, like even with 5,000 data sets, as you can see, it took like 4 hours to run. And what if I want to train it more, right? Because there's like very little data sets, and it's not really clear that it's like helping the model learn a lot. And also the noise that I added at the start, it probably made the model quite susceptible to the noise itself, which is too strong for the model to actually learn and actually start identifying which is adversarial and which is not. And that was quite difficult, right? And then there's also the attack curriculum was kind of abrupt, like, due to my lack of expertise in this domain. I jumped straight into the CW component, right, in a compounding attack, which makes it quite difficult for the model to actually learn before they can even start treating all this data set properly. And lastly, there's also like the alpha and beta, where the weightage to the quantum part and also the weightage to the CNN, if it's like too inconsistent, because the data sets are very noisy and the model can't really decide on which part to actually emphasize on, right? So like given more time and more resources and compute power, I think that I will definitely produce a better result. But given that my lack of expertise in this knowledge, this domain, and the complexity required for this one that I did not oversee, it did not achieve my standards of producing a good result here. But it is a good experience, and yeah, thanks for listening.